concurrency control.
Sorry.
I'm going to start anyway here. So people have asked me if this is a very technical talk, and the answer is yes and no. I'm trying to keep it as high level as possible, but there's definitely a little bit of technical stuff we have to get into. If you get into the depths of how Postgres actually does MVCC, it's a big hole into more and more complex things. So I'm just skimming the top, trust me. There's a lot of stuff in there. So MVCC, of course, is the way that Postgres handles the concurrency issue, which is you have your data and you have more than one person wanting to look at the same data at the same time. There's a lot of oversimplifications in this talk, so don't hold those against me if you know the topic very well. And the idea of MVCC is that we maintain separate copies of any data that is modifiable. And of course, the main thing people say is readers don't block writers and writers don't block readers. So MVCC is one method of attaining that goal. There's other methods, other databases use, and they're generally worse. The only other real option people use is locking, heavy locking. So if you want to update a row, you block that row. Nobody else can even look at it, make changes themselves. They hit it. MVCC is a much better way of going about things.
I don't have anything to write with, but if you go to, you guys ready for URL? It's smarterbythemonth.com/MVCC. smarterbythemonth.com/MVCC. Reload.
Anybody have a flashlight, please?
Negative.
You have to keep pressing on this.
That's okay.
For 5 seconds.
Disconnect it from your laptop.
All right, we're going to move on the best we can in the interest of time. So to understand multi-version concurrency control, we really have to understand how Postgres stores the data physically on the disk. And that's what we'll get into a little bit. Basically, you have your data directory everybody knows about. There's a subdirectory called base underneath that. And there's databases underneath that, other subdirectories. Inside those, there's other files that represent each table in the database. And these are all numbers, they're not named. Inside that table is a concept called pages. And that's the internal grouping that Postgres uses to store one or more rows. And okay. No,
yeah, if you just double click on
Yay! Boo! It went away. What happened?
I can sit here in advanced slides.
It's gone again.
Where'd it go?
Picture muting on.
It said picture muting on. Whatever the hell that means.
The picture was very loud.
Yay!
So I probably should
It ain't broke right now.
on.
Here it
Don't
is.
touch
So
anything.
I will babysit.
Okay. So here's what we were talking about before. Is that laser pointing back to Jim? No matter. So this is how it's arranged inside Postgres internally on the disk. And this is an analogy I like to use in that we have a monastery. These monks are responsible for handing you the data. They're the brains behind Postgres. You can think of library as equivalent to the base directory. A wing is the database section, but most importantly, thank you, sir.
The non-NN.
Ah, there we go. So most importantly, you can consider pages as shelves in a library, and the books are the rows, also known as tuples, that Postgres stores.
Ooh.
So basically, this is the analogy we have here. We have 2 pages, also known as two shelves, and they're numbered within Postgres, starting at 0 and 1. So this is page 0, this is page 1. And inside each of those, we have a bunch of slots to hold the books, or the rows.
Sorry.
That's all right. So Postgres has an internal column called CTID that always shows up if you ask for it specifically, but not show up if you select star. It's like OIDs. Well, still is, but we shouldn't be using OID. So for this example, and these examples follow, we're creating a table called monk with a single column A. We're going to insert a single row into it, and then we're going to select not just star, but the CTID. We're going to take a look. So CTID format is the page and then the offset in the page. So this is at page 0, the first slot. And we insert a couple more values. We can see that they're pretty much stacked in order. 1, 2, 3. Thank you. So this is what it looks like inside the database, grossly simplified. But we're at page 0, and we have 3 rows, which each contain data, 1, 2, and 3. Next, please. So let's see what happens when we update. So we're going to take row 2 and change it to uppercase. And then we're going to also insert a 4th value. If we look after we do that, we see that we have 1, 3, 4, and 5. The reason for that is when we changed 2, 2 actually became this 0, 4. And then we inserted another one, and the next available slot was 0, 5. So why didn't it reuse 0, 2? Because it's a dead tuple, and it's not the responsibility of this program or this session to do the housekeeping to say you can use 0, 2 again. That, of course, is vacuum's job. So this is the state of things right now. We have, in the first page, we have 5 rows, 5 slots. This one has been marked dead. So what we did when we updated that 2 to the uppercase 2 is we took the original one and we marked it. There's a special flag. I won't get into all the headers, but we marked it as deleted, basically. And then we created a brand new one. That's a copy of this, but with the changed information. And it does this even if you don't change anything. Is there a question?
Yeah, I'm just trying to make sure I understand. You're talking about marking it as dead. My, vague understanding how this stuff works is that you're actually marking it with a particular transaction ID.
Yeah, we'll get there.
Okay. Okay. It's kind of, okay.
All right. Next slide. So we'll take a look at what vacuum does in this situation. Here's our original. Oh, the original's not there anymore. That's all right. So once we do the vacuum, we look, we have 1, 3, 4, 5, same as always. We insert another value. And now 1, 3, 4, 5, 6. So it looks as though vacuum hasn't done anything, but it actually has. And I'll get to why we don't see 0, 2 show up again. But basically, previous slide.
Oh, sorry.
So basically, vacuum's job is to do the cleanup. And in this case, what it's going to do is say, okay, nobody's using this row anymore. It's dead. And it checks to see if any other sessions might possibly be still looking at that row. And if it isn't, it basically pulls that book out of the bookshelf and says, okay, this slot's free again. All right. And one more. So I did dump the output of what vacuum actually says. This is a verbose thing where I'll used to, but the important thing here is it found one removable row. That's that dead one. 4 were not removable. And I just wanted to quickly point out that you often see these PG toast tables, and the reason for that is that Postgres only stores so much data in the original layout you see with the page. If it thinks that there might be more data than it can handle natively, it creates a toast table which has its own index, and that basically is a way of externalizing data in a column that gets really large. So you notice I did a text one and it showed up. Next one, please. So just to illustrate this a little further, that depends on the size. A little to the left, keep that. So we're creating a table called toasted with varchar 100, and then we're doing a vacuum of it. And if you notice, the only thing we vacuumed is the table itself. But if I recreate it with the varchar of 550, do the vacuum, suddenly I've got all sorts of toast going on. So there actually is a difference between varchar 100 and varchar 550 in that Postgres is saying, well, you might eventually hold 500 characters, and I can't guarantee that I can hold it in the way I'd like to hold it, so I'm going to create a toast externally.
Sorry.
No, that's fine. All right, so we are here. We're going to delete the first entry, which is at slot 01. We're going to vacuum right afterwards, which should mark it as available for reuse. And then we're going to insert again into the table with a value of 5, and we get this. You notice that slot 01 is now occupied by the one we just inserted. Next slide, please. So before I get too much further, actually let's pop ahead one more slide. I might have it written out. One more slide. Okay, so with MVCC, we never update a row. That's the major thing you should take away from this. There is no update. There is simply delete and make a copy and insert a new row. And the reason for that is we don't want any contention. We can't really update something if we have a lot of people looking at things at the same time. We just create copies, and then everybody, internally there's a lot of little numbers that tell you which of those rows are visible to you. But the important thing is, since we're just deleting and inserting, we're not updating, it's always quick and efficient for anyone out there to get a stable view of all the rows that they should see. We'll get into that in a little bit more. So, the next one. So, I was kind of glossing over things before, and I'll get a little more detail with my ugly GIMP graphics here. The data itself is actually stored on the right side of the shelf, you could say, and the CTID numbers we see are actually offsets. There's a specific number of bytes. So if Postgres says, I know something's at 2, it knows how many bytes to jump forward, and at 2, there's actually a pointer to the actual data itself, which is off to the right. Next slide. Thank you. Now, on the slides we've shown so far, all the books are uniform length, but I just want to point out that pages are not predictable as to how many rows they can hold. Pages are a certain fixed width. Usually it's 8,192 bytes, but you can compile Postgres to do something different. Don't do that. If you do that, you have a hard time jumping to a different system. So in this example, I'm just inserting ABC 256 times, and then we're going to look at the CTID, all the ones I inserted. And as you can see, we get up to 255 values from the first page, then we start filling the second page at 1-1. And in this example, I'm going to add an additional 150 rows, but this one's a little bit longer. So the books are a little wider. So they don't fit quite as many. If you look, shelf 1 stops at 146 books before it wraps to shelf 2. So the takeaway is that you can't predict the size of a page as far as how many rows are in it, dead or otherwise. So this is just the same thing. If we look at a single row and we look at the size of the table as computed by Postgres, it's 8,192 bytes. Obviously, storing 3 letters is not taking up that much room. It's because everything is done by page. So that's the size of a single page. In this case, because I've truncated, the page holds a single book. Now, if we do the same thing, but we insert 1,000 times, obviously we see that we have increased quite a bit. So that represents more pages. Now, we do a vacuum, and of course, vacuum is, if you notice, we did a rollback here. So we didn't put the rows in the database, but we did. We put them in and we marked them as don't use them. They're gone, they're dead. That's what rollback does. So when rollback, we're not physically aborting rolling back as if it never existed. We're still creating all the rows and we're marking them as dead. And the reason for that is just efficiency. It's not anybody but vacuum's job to do all the housekeeping and delete and free up all the books that can be used again. So we notice that vacuum does do its job quite well in that we have a temporary blow with 1,000 values that don't really exist, they're dead to everyone. Once we vacuum, we're back down to our small size.
Correct question on that, if you go back to the previous slide. When you insert 1,000 rows, it only goes from, I think, about 8192 to about 4 times that page. So does it put actually multiple rows into the same page?
Yes. Yeah, there's multiple books each shelf. Next. So, I got this earlier, but the rule of MVCC is there are no updates. That's just a construct, a convenience, as far as Postgres and MVCC is concerned. It does a delete, and then it does an insert. So the question becomes, which set of books do you see? And this is where MVCC really shines. We are updating, in this example, we're going to update this row into a new value. So 2 gets marked as deleted, and 5 gets marked as inserted. So what we see, if we do immediate select again, is we see 1, 3, 4, and 5. There's some internal markers on 2 that says, don't look at this row. Someone else, another transaction, we'll get into the details later, sees 1, 2, 3, 4. And that has to do with the visibility rules. Next, please. So the way Postgres handles visibility rules is it gets a snapshot of the database. You've probably heard that everybody gets a copy of the database. What it actually does is when you start a transaction, you get assigned a transaction number, which is a sequential number that is internal to the database. And you also get a list of all other transactions that are open right now. And 8.3 adds these nifty little functions, transaction ID current and transaction ID current snapshot. And we can take full advantage of those. Next, please, to take a peek at what's going on. So here we're just beginning a transaction. We're calling transaction ID current 2 times. You notice we have the same transaction ID. We get out of that transaction, and now we call it again, we have a different transaction ID. And if you notice, it's still incrementing because these are both implicit transactions right here. So because we're not in the begin commit, we've actually incremented our counter, we have a new one. Next, please.
So select the new way select doesn't have to, doesn't continue to transaction.
Right.
Because it's not defined.
Yeah, but that's actually a function that we're calling the transaction current. So it does some stuff. And if you notice here, transaction current snapshot is basically a list of all transactions that are interesting to you. This is the minimum and this is the maximum of all open transactions that you care about. In this case, we're the only person in the database. And the third row has a list of transactions between these two numbers that are actually active at the time you started your transaction.
So if you had more than one session going and they both opened up transactions, the one that opened up first would see the transaction ID, the second one was open. Well, while they were both open, they'd see.
Other way around.
Yeah.
Okay, yeah.
Yeah, I'll show you an example of that in a minute. Back one. No problem. Okay, so we come out of the transaction and we notice we immediately have a we increment both the minimum and the maximum, which happens to be our own. We call it 2 times in a row. This one for some reason is not automatically increment. Just a little something to be aware of. I'm not sure why I poked around in the code, but transaction ID current will increment as if it's doing something in the database that warrants a new transaction. Transaction ID current snapshot does not. I have a theory about it. I'll get it wrong by saying it out loud. Let's look at this one. So in MVCC, there's actually 4 types of things you want to watch out for as defined by the documentation, and there's 4 different possible states you can be in. But at the end of the day, Postgres only has 2 states that you need to worry about: read committed and serializable. Now, read committed is the default state, unless you specifically set your database to be something else in your PostgreSQL. And serializable is it's really strict big brother. And the difference between the two, as you can guess, read committed allows you to read other transactions that have committed since you started. So, dirty secret number 1, people don't realize Postgres is not ACID by default. And in particular, we don't respect the I, the isolation. In a read committed state, we are not isolated. So you start a transaction, you can get a list of rows. You say, give me those same rows again. It could be different because someone else might have committed while you did that. Serializable, on the other hand, is strict ACID. And whatever you see at the beginning of your transaction is what you see. In other words, your snapshot of the database remains the same throughout your entire transaction.
Question about that?
Yes.
So, is that due to the SQL standard or the SQL standard? The reason why read committed is default?
I don't know if it defines it, to be honest.
It's practical. It's practical to make it default. I'm not aware of any database that has the default serialized.
Is that the case even if you do begin transaction and do 2 select statements? Because you're not incrementing the...
Yeah, it has to do with your isolation. I mean, in the beginning you can specify the isolation.
Yeah, well, you can see right here. There's a transaction 1 is beginning. Transaction 2, and these are time-based. Transaction 2 begins after that. Transaction 2 says how many rows are in the home table? 0. First transaction inserts a row, does a commit. We run the same select again. Within that transaction, we have a different number. This is read committed. This one is committed, so we can read that commit. Next slide. This is just showing the same thing, but with some transactions IDs. So we start at 21421. We begin. We are 21422. Oh, okay, I'm sorry. The point of this slide is the transaction ID is assigned when you first do something. It's not assigned when you actually say a begin. So if you notice here, we're at 21, and we begin the transaction. So we did not get assigned 22. This guy that started after us got assigned 22 by doing something. We did something, and then we checked, and we've got 23. So the point to remember is you don't have a transaction ID assigned to you until you actually do something for the first time in a transaction. Next. All right, we're gonna look at transaction ID current snapshot with the same thing we did before, the select count that changes. And this is saying we're transaction 470, and the minimum and maximum we care about are in the range 470 to 470, which is just us. And this one is saying the same thing. It's another transaction, except we're 71, but if you notice, 470 is our new minimum and maximum that we care about, because this transaction is still open.
Why is it not 470 and 471?
It's an optimization that Postgres does.
Oh, until you've actually done anything that matters there, it doesn't?
Well, it actually, technically, this should say 214071 as well on this side.
Yeah,
But there's some sort of internal optimization, or it's a choice they made in writing this function that it doesn't show up if you're right next to it sequentially. So I don't know if that's, if it's this function not showing it, or if it's just relying on Postgres doing lots of tricks. And there's, with MVCC and all this stuff, there's tons of little tricks and hints and all sorts of things throughout Postgres to make this work really, really efficiently. It's also very, very complicated. Now, if you notice, after this one is committed, we get that different count, and we are still 471. But if you notice, these two numbers have changed. And this is what allows us, right here, to see this commit. So the book, we'll get to that in a second, the book that represents this row actually gets marked with the transaction ID that does it. So in this case, 470 is saying you can see all transactions that are less than 470. So in this case, you're saying I can see all transactions that are less than 471, which now includes 470, which is just committed. Now this is read committed, and the thing that really defines read committed is the snapshot information changes from one moment to the next. And it changes every single time you run a command. So it has a potential to it, it needs to change. So this is why read committed is read committed, because these two numbers change. And these two numbers indicate which rows you can see in the database. Next slide. I'll clear it up a little. Now this is serializable mode. And the difference is, it's the exact same thing except we're saying, okay, I want to be serializable. So we do the same thing, we insert a row as really marked as 474. We can't see 474 yet because it's not less than 474, so we have 0 rows. However, once it's committed, this is now 0. And why? Because these two numbers are exactly the same. In serializable mode, these two numbers never change, well neither does this one. And that's the definition of serializable mode. You get a range one time when you start a transaction, and it stays there until you commit. So I alluded to the information earlier. This is a book representing a row of data. So most of the book is taken up by the data, but there's a lot of information that's stored in the header of each tuple on the disk, also in the book. Two of the most important ones are xmin and xmax. Xmin records the transaction ID that created that row. And the basic rule for MVCC is, and this is glossing over lots of details, you are assigned a range of xmins that you can see. Generally, you're given a range like 1, 2, 3, and the rule is if it's less than 1, 2, 3, you can see it. So Postgres walks through for a sequential scan, looks at each of these books and says, hey, are you allowed to see this book based on the xmin? And if it's less than that magic number, you can. If it's greater than, you kind of can too. That's complicated. Xmax has a similar function, and it's the transaction that deleted this row. And it's also used for locking. And there's a bunch of other little things all in the header that indicate the status of this book right now. There's some things that vacuum uses, And it's incredibly efficient. I think it's down to 23 bytes right now. It varies. But it's really neat the way they do it because some of these fields are overloaded. Some of them are bit fields, and they store an incredible amount of information in that 23 bytes. But that's understandable because every single row is going to take up 23 bytes of overhead in your database. You want to make it as small as possible. Next, please. Okay, this is still sequential. I just wanted to make the slides rise up a little higher so I didn't alternate them. This is demonstrating in addition to CTID, you can actually view the xmin and the xmax for a row in a database directly. So two more hidden fields to be aware of. Xmin and xmax, we can see we inserted a value called red. We are 2470. Okay, do the commit. And if we look, we see that 2470 is the transaction that committed this row, or did the insert for this row. Xmax is 0 because it hasn't been deleted or locked yet, at least to us. There's our old friend CTID, which says we're in page 0, slot 1. Actually, I'm sorry, this should be red, not 1. And this would see the same thing, basically. Next slide. Real quick, I'm going to say a few words about two-part commit. It's fairly simple. The idea with two-part commit is you're in a transaction, you make your changes, and then you say prepare transaction. Go to the next slide. So we're in a transaction, we do some stuff, we say prepare the transaction. What it does is it doesn't do the final commit. The final bit that says, you know, all these rows are live and ready to go. It stores it on disk in a separate transaction, a separate directory. At that point, the moment you say prepare transaction, it's like a delayed commit. You're no longer in that transaction. So I say commit again, and it says, oh, you're not even in a transaction. Two-part commit, if you notice, we go over here, we have another session that says, okay, I'm 21475, but if you notice, 21470 is still hanging out there. So this is saying you can't see basically 21470 yet because you can only see things that are less than this number. So 21470 is still hanging out, hasn't committed yet. And that's what two-part commit does. Next slide. I'm sorry, previous slide, there's nothing there.
Good question. At a high level, what is two-part commit?
Previous slide. Two-part commit is mostly used for replication when you have two databases that you're making changes to at the same time. Basically allows you to make all the changes on one, all the changes on another, and do everything except for that last final commit. So then you, once both databases come back and say, okay, we're all ready to go, you issue a commit prepared or a rollback commit prepared on both the databases. And the idea is you're reducing the window of when they're different because all the work is done. It's just that final little twitch you can do to both databases as synchronously as possible.
In your example where you have the serial envelope, what happens if when you're doing two inserts or two updates and they conflict with each other in the constraint?
Still block.
Great. When does that transaction show up, you mentioned?
When is what?
When you do that prepared transaction, when will it show up? Like when all that is a committed at that point?
Oh, you do an explicit command called commit prepared or rollback prepared. Or commit prepared in the name of it. You give it an arbitrary name for your transaction. And there's a system table you can look. Generally, you don't want those hanging out. This is only really useful for replication. So you're going to prepare the commit on both sides and you're immediately going to release it. Sir?
Something that you may want to know about this in case you're tempted to go away and use it is that the locks stick around. When you've done that commit prepared, all the locks that transaction has taken stay there until you commit or rollback prepared. And so if the other machine crashes while you've got this, it actually reboots and comes back to life with all of those locks in place. This is a very, very heavyweight mechanism. So before you go home and use this, make sure you read all the documentation about it. It's very expensive. I don't want to sort of take your time.
Yeah, if you're not writing your own replication system. So there's a few things you can't do with two-part commit. I should just point these out really quick. There's a few limitations. Obviously, temp tables, listen, notify, things that are dependent on, you can't really push them off to later. Next. So let's talk about indexes. This is where it gets more interesting. The great trade-off Postgres made with indexes is it doesn't store all that visibility information. The indexes don't. So when you use an index just says, okay, you need to go back to this point in the bookshelf to get the data. Even though the data might also exist in the index, you always need to go back to the bookshelf to check if you can see that book. Because the visibility information, those X-mins and those X-maxes are only stored on the bookshelf in the page, which is called heap, as opposed to the index. Next. So basically how an index works is it's a separate construct in the database. This is a crude representation of a B tree. And you look something up, it goes through the B tree, and then it says, okay, I found it. And what's stored is the CTID that we've seen before, which is a physical location on the disk of where that information is. This is a little oversimplified, but basically, so when you're running a select and you hit the index, it uses the index to find where it is. It goes up, it says, okay, I'm going to count over to 1, and then 1's going to tell me where I should look at the rest of the page to get the data itself. And then it's as if it did a sequential scan. It looks at that row and says, am I allowed to see it? If so, it gets returned. If not, it doesn't. The next
Question. If not, it doesn't, and it looks in the index for another place that it exists, and it.
No, the index will be authoritative. It says this is where it is.
So then you ask for something, transactions in progress, you don't get it, or you get told, no, there's transaction in progress, it's locked away with MVCC, should you receive something? Go on, not understanding, I probably will.
I think I kind of understand it. You're talking about how, kind of like, well, when does the index get updated? If you're inserting something that's not committed, is it in the index, or?
Well, the index will still point to the old row, but that's fine, because the old row, the old heap row, still has, is still authoritative for that session. No, I missed a little blackboard on here. Yeah, I wanted to, let's go back. What did you slide through the table? Let's try to insert it. No, okay. I'll just demo this the best I can. And I was meaning to do this before the projected problems. So I was oversimplifying things a little bit as far as what a page contains. Postgres actually tries to be very efficient inside its pages. A page has all these little pointers right here that start on the left-hand side, and then it fills in the data blocks from the right-hand side. So there's a big, not in this example, but this is the free space of the page. So when a new row is added, we have to add a pointer, which gets added from this end, and we have to add a page, which gets added from this end. So to give you an idea of, that's what we did. vacuum full. So what vacuum full does is it doesn't just take out the books and says you can reuse them. It's like the monk coming up to the bookshelf, putting his hands to the left-hand side and just shoving the books over, compacting them. So there's no more empty spaces. And I'll do this more quick, but I was going to show an example of how we ended up with a particular CTIDs that we did. No, it's in there. There it is. Okay. So we just did a vacuum full. So the question is, why don't we have 0, 1, 0, 2, 0, 3, 0, 4? Because that would seem to be the most efficient way. The answer is, it is still efficient, but it has to do with the fact that these pointers, such as 0, 2, are pointing not necessarily in order, but they are in order as far as the compaction goes. And the best way to understand that is, if this is the original state, we have 5, capital 2, a 3, and we have these 2 deleted pages. What vacuum full does is it says, I'm going to start over here because I want to maximize the free space of that page. I've got a slot over here. I'm going to take 5. I'm going to put 5 over here. It says, okay, I've got another free space. I'm going to put this one over here. So, without getting into elaborate diagrams, that's why this is 0, 2, 0, 3, 0, 5, 0, 6. It doesn't look like it's compacted, but because of the way this is moved around, 2, 3, 4, and 5 are actually from the right, 2, 3, 4, and 5, efficiently packed. So that's basically what vacuum full does, again, oversimplified. But it moves things around, and the idea is we want to keep the space in the middle as large as possible, so we can pack efficiently more pointers and more pages into it. All right.
So does that also allow you to avoid updating the indexes for the tuples you're just shuffling around in the page that weren't?
That's hot. I'll get to that.
Well, so the indexes of the tuples that you aren't actually updating, I'm not talking any tuple that you update, you need to update the index as well, except for the case of hot.
Right.
But in this case, for instance, you wouldn't want to say, 1, 2, 3, 4, because then you would have to update tuples like 5. You'd have to update all the indexes that point to that tuple.
Right. I guess I should be clear on that. What happens is, number 5 here, let's say it's pointed to originally by 2. So, position 2, which is 0, 2, there's a pointer at that point in memory that says, this is where on the page number 5 is. Now the index has a pointer to 0, 2. That's its canonical lookup. Now when vacuum full does all this rearrangement, all that happens is this internal number gets changed to point to this part of the page. It says that's where we should start to look for the data for that row. So the index doesn't need to change at all. It's still pointing to 0, 2.
Okay, abstraction.
The pointers in the block header, they're only pointers within the block. They don't point to other blocks. So there's no, the index is referring to the block as well as the slot.
Yeah, these are small. I think they're 4 bytes. This whole thing. Two-part commit real quick. Oh, that's too far. Those pointers, I know we were there. Sorry, folks.
This is just a little review.
Yeah. Soak it in. And apparently these are now on the web. All right, so that's the book. Two-part commit. Two-part commit example indexes, great trade-offs, how indexes work. Okay, here's what works. A few more notes on indexes. Indexes don't get cleaned up or compacted when you do a vacuum. Vacuum only cares about the heap, about the visibility stuff. Its job is either mark or pull a book out and mark it as reused, or to reshuffle all the books. But indexes are actually, most of them are B trees, so there's no need to vacuum it per se, but occasionally you will need to re-index, and that's how you eliminate bloat. And I should point out that that bloat, the problem that vacuum solves is basically when you have all these dead rows. They're just building up and creating huge pages on disk that are only holding a little bit of data. So it's not very efficient. So reindex is the way to get rid of index bloat, which is a very rare problem. Reindex does not really need to be run in most cases. It's rare that you need it. There's actually two other hidden columns you can look at called CMIN and CMAX. And those are just internal counters for the command ID. So if you do 12 inserts, they'll be labeled internally 1 through 12. It's not that important for our talk today.
And those sequences are unique per transaction?
Yeah, they're very temporary.
Yeah.
They don't,
I mean, each transaction gets to start,
Yeah.
starts with one and move on.
yeah, it's just some internal housekeeping, basically. Indexes, there's a lot of different types, and basically, it's not well defined like this page, the heap thing. There's just an API for how to create the indexes. Something that's coming in the future, someone submitted a patch for something called a thick index. And a thick index is actually a different approach where the visibility information will be stored on the index. So it's an alternative form of index. So if you're saying, if you're doing an index search for the word red, and that's all you want to get back, and it's in the index. The old way is it says, okay, red, I know that's at 02, and it points it there. With a thick index, it's actually going to store Xmin and Xmin, or the equivalent of them, and say, okay, red is what you want, red is what you get, and it completely avoids having the index go back to the disk.
Wouldn't that solve the problem with count stars not being able to hit the index?
Yes.
Awesome.
Well,
but there's a drawback in that you can no longer make this assumption safely. In other words, every time you make an update, not only do you have to update the Xmin and Xmax of the heap, every single index, every thick index has to be updated as well. And that's why visibility information is not in the index. It's inefficient as far as we have to go back to the page every single time, but we don't have to update every single index every time we make an update as well. So that's the trade-off Postgres made, and thick index is an option to get people to do it a different way. They're willing to absorb the cost.
So I had a couple of questions, maybe a comment. First question was the thick index. I mean, does the API for indexes actually have a mechanism to allow that, or is that being changed?
No, it's a core change.
Well, yeah, I'm just wondering.
To the internal index code. So.
I mean, you're gonna have to, yeah, and you're gonna have to have probably, I would think, I assume that you're gonna have the ability to have both thick and not thick indexes on the same table.
Yeah, the default will be regular ones, and then you can create thick ones if you want.
Now, it doesn't. I also want to say I don't think it completely solves the count star problem. I mean, scanning an index, if it's 500 megs because you've got a 3 gig table or what have you, is still scanning 500 megs. It's a lot faster.
Yeah.
But it's not what some of these other databases do, I don't think, where they keep some kind of internal tracking of basically the number of tuples.
Right.
That you can see where it's just instantaneous.
For an MVCC architecture, you can't have just a single number kept. This is
right.
as close as you can get to it.
You can. It's expensive and difficult to do.
I mean, yeah.
So MySQL actually does store a number, so their select counts are very fast.
Right, but they don't have a fully MVCC
right.
architecture either.
And there's cost associated with doing that as well.
I just want to point out that this does not mean that you can go start doing, loops of select count stars. All right, it's not, it's better, but.
I was just going to add that the dead space map or the visibility map or whatever, also that work could also solve a similar problem in a different way. The keeping track of what tuples might have dead space on, and those would be the only ones you need to check.
Right. Yeah, there's actually, each page has its own header, which I didn't really say. There's a lot of meta information about that page. It actually contains hints and things. It tells it, you know, maybe you don't need to scan this page like the vacuum. It says, you know, there's probably no interesting rows, so you don't even need to iterate through them. It's just one of those little micro optimizations that's throughout the code. So I alluded to HUT, which is a new thing that 8.3 has. And let me see. So HUT stands for heap only tuples. And the traditional way, as we mentioned, an index has an entry that tells it where to go. In this case, it goes to here. And this one says, okay, you are looking at this page right here. So with heap only tuples, anytime you do an update, I'm sorry, let's say the normal case. We do an update that changes things around. So we basically say, this row is dead to us, here's the new row, we just did an update. And it's at position 4. So right now, what happens, or pre-A3, we also have to change this. So we have to go and change the index itself and say, you're now pointing to 0, 4. So what HUT does is allows no change to the index at all. It keeps this one around, or more specifically, it keeps this a pointer. So at this point it says 0, 2 after the update. It goes to 0, 2. 0, 2 is deleted, it's no longer authoritative, but it has a pointer that says, okay, what you really want to go here. And this is a heap only tuple. That's where the name comes from, because this only exists on the heap. The indexes are still pointing here. And it's actually really clever. What it does is because even if the associated, let's say this one, the data itself gets erased, we keep around a little pointer. And everything else is deleted. But there's still a little pointer that says go to 4. So what you end up with, if you do a lot of updates and you have heap only tuples, this is still pointing to 0, 2. But as you do the updates, there's a whole bunch of little chains, and this is very efficient because they're just pointing to each other. So they point, until they finally get to the one, the heap only tuple. That's actually the authoritative one, and that points to the actual row. And there's a lot of sub-optimizations, and these aren't well defined as to when they happen. It's sort of like an auto vacuum sort of thing. But it's smart enough, it sees a bunch of these, eventually it'll say, you know what? We don't need any of those, because what you're really doing is this. So it cuts out all the middlemen, and they can get totally deleted, frees up more room.
Doesn't HUT work across pages though?
No.
No? No, not at all? Okay.
No, yeah. Pages are pretty strict. A row never does a partial page, and HUT will never cross a page. If it runs out of room, it'll just it'll update this.
It'll update the index?
Yeah.
Okay.
That redirecting the pointers, is that part done by vacuum, or is that when it goes to allocate another heap only?
It's done right away when you do the update. And there's some complications with create index and there's and vacuum, but I won't get into that. I'll just say HUT is really cool. So basically what it does is it says if you're updating your table and the row and you have an index that isn't, how to put this, you don't have to change any indexes that aren't related to changes you made. Now, if we updated something important, like we changed green to red, and we're actually have an index on that, obviously, the B tree is going to change. But if we're changing green to red, and this, this is for an ID column, it's totally unrelated, it doesn't care. There's no reason treat the change. Hut says, okay, let's not even change anything about the index. You don't have to touch it at all. So the idea is you make an update, and in theory, you only have to change the indexes if you absolutely have to. And this is a huge boost for A3.
So, wouldn't it be ideal to only partially fill pages before allocating another page? Like if you sequentially create pages and fill them out, create another page, then I don't think would be able to make use of HOT because you wouldn't have any space on that page. So, am I?
That's another A3 feature.
Oh, sweet.
Good question.
Yeah, I mean, there's all sorts of optimizations that could be made. Right now, even, let's not worry about that.
There's a fill factor on table creation and index creation, this case too.
Is that right?
Yeah.
I didn't see that.
But
So
yeah,
they-
going back to that same thing, if you update a row 10 times, you still have to keep all 10 rows of them, which would mean that you will overflow from that page.
Well,
Yeah,
if you
if
hold
you
one
don't
to
fix
10,
it,
these pointers, it'll turn into just these pointers. It won't worry about the rest of the stuff. These pointers are very small. So you can get 20 of these pointers for maybe, one of these slots of data. So remember, we're filling filling the tuples from the right and these pointers from the left. Filling up our free space. But these are very small. And like I said, they collapse. So if you did 10 updates, what it would do is it would say, don't worry about these middle 9. Just point to the last one.
no, I'm talking about like the page, the rows themselves populating the whole pages, and you're still doing updates, and it goes to an overflow mode. The next update would then go to the next page, and it will have to go back to the next.
Yeah, so what he was saying is it won't always solve the case, because sometimes you'll run out of room, and you have to create a new row down here. And in that case, we do have to change it, because we won't point from this page to this page. Things rarely cross pages. And Postgres is designed, that's the efficient chunk that it always grabs. It's a page of information. Next, please.
Can I add, one thing about HOT is it's still useful because if you have one tuple that's updated many times very quickly, that was a very bad case in A2 and before. But in this case, even if the page is full, if it has to go to the next page, then now you've got a new fresh page with 100% free space, and you get 200 free updates or something, or however many you can.
All right, so I'm going to switch to system tables, PG, class, and friends. And they, third secret number 2, they are not MVCC. What happens with the system tables is, well, the system tables themselves are, but internally, Postgres always wants to know exactly the state of the system tables and system information right now, and it needs to know that. So they are not technically MVCC. Go to the next slide, we'll demonstrate that. This shows why that is. So transaction 1 begins, and then transaction 2 begins. We do an alter table on month. We're going to add a row size column with a not null default M. And you can assume it's a serialized or recommitted. Doesn't matter. So we commit, and at this point, the database has a new row, a new column to that table. However, this transaction, when it started, did not know about that column. However, if it does an update month and creates new pages, it needs to know about that column right away. So internally, everything's updated instantly. It gets what's called a snapshot now. Because technically, this transaction should respect the fact that it can't see anything except what it saw when it started. But in reality, we can't do that for the system tables. We can't drop indexes and create indexes and alter table willy-nilly, because everything needs to know what to do at that moment.
Open recommitted if picked up the change at this point?
Recommitted would, but serializable
Okay.
would. It's the same thing. Next slide. Okay. So There is some automatic locking when you're messing around with the system tables, you're doing alter column and things like that, that protect you most of the time. So you don't need to worry about this implementation detail. But if you are messing with the system catalog, it's something you need to be aware of. I speak from painful experience. Both Sloaney and Ricardo run into this problem in that turning off triggers is very expensive because it does a lock on the table that you're turning off the triggers on. You do an alter table, disable triggers all. And in a production system, that's just not a good way. So we both hack the PG class and other tables directly, update PG class, set a column. But the danger is you can't do that without setting a lock to be completely safe. And that's because the system tables are not MVCC. They are constantly getting a up-to-date representation of the system as it exists. But this problem has actually been solved in 8.3. There's something you can say set session replica role to replica, and it's just a little hook that Jan invented to turn off all triggers and rules in a non-locking, non-blocking way. It just basically throws that hook in there, and when it comes around the triggers and rules, it just doesn't run them. And obviously, you should use this carefully. And there are triggers. You can set classes of triggers now, basically, and say, these ones should fire, these ones should not. It's quite handy if you're writing applications with them. Next. If you're really interested in this stuff, as I mentioned, there's all sorts of optimizations and tweaks. These are the files that are involved for the most part. This one defines the heap tuple and defines basically the format of the page. And as I said, there's a lot of stuff I glossed over. There's a lot of meta information in the head of the page. There's a lot of meta information in the head of each tuple. T-qual basically is the routines that determine visibility. So if you really want